Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to continue our conversation about colligative properties by talking about freezing point depression and boiling point elevation. So as a reminder, when we're talking about colligative properties, what we're really talking about is a property that only depends upon the identity of the solvent and the amount of solute I've added to it. So Raoult's law is a classic example of a colligative property because the vapor pressure of the solvent depends upon the solvent, and the concentration, as I add more solute, we lower the concentration of the solvent, which affects things like vapor pressure. But it turns out it ends up affecting any number of other properties as well. And the reason why is that as I end up adding more solute, the solvent essentially becomes more stable due to entropy. It is more entropically disordered. So as a result, we have things such as the vapor pressure lowering because as a whole, colligative properties are dominated by this idea that outside solvent molecules want to join the party. So if I've got molecules in the vapor phase, they want to join the party in the solution. If I've got molecules in a solid, they want to join the party in solution. And if I have pure solvent, it's going to want to join the party. Everybody wants to be where it's happening. And that's really what a colligative property is all about. Essentially, what ends up happening is I add more solute to a liquid solvent by changing that entropy, making the system a little bit more disordered without really affecting the enthalpy. What I do is essentially widen the stable region in the phase diagram. So now it's going to be a little bit more likely to, the system's going to be a little bit more likely to be liquid than solid. So it'll be liquid to lower temperatures. It will also be a liquid to higher temperatures on the vapor side. So as a result, what ends up happening is we end up increasing the boiling point and reducing or lowering the freezing point. So this gives us two big properties: boiling point elevation and freezing point depression. So if we're looking at boiling point elevation, really what we're happening, as I stabilize this liquid, it's going to take more energy to get that vapor up to 1 atm. And we saw this a little bit with Raoult's law, because I end up producing less vapor the more contaminated I am. So as a result, I'm going to have to get to a higher temperature to get that lower vapor levels up. And we can track the increase of boiling point by looking at the molality of the solute. So again, we can do some mathematical tricks, but more or less what we're turning is mole fraction of the solvent into a molality of the solute. And it turns out to work out pretty well, because mathematically this gives us a nice, good concert calculation, because now if I know how much solute I add, I can turn this into an amount of solvent. So it's a good property that relates solute and solvent. And this is the reason why molarity or mole fraction doesn't work quite as well. So as a result, as I increase the molality of the solute, I'm going to increase the boiling point by delta T. So delta TV is going to represent exactly how much I've increased the boiling point. And they're going to be related with a proportionality constant. So this is called the boiling point elevation constant. And it turns out the only thing it depends upon is the identity of the solvent. So every solvent will always have the same exact boiling point elevation, no matter what solute I added to it. So for example, for water, this value is going to be about 0.51. So this is actually a fairly useful idea. And in fact, one of the useful advantages of things like boiling point elevation is if I add more and more, I can figure out exactly how much solute I've added to a system, or how many moles of solute I've added, simply by measuring the change in boiling point. And this is a trick that's occasionally used to determine the identity of the solute being added. If you know the mass, you can determine the moles. Similarly, on the other side, as I add more solute, the solvent becomes much more difficult to freeze. So I'm going to reduce or depress the freezing point. And this is called freezing point depression. And you'll note that change in the temperature will be negative here, but again, will still depend upon molality. And we've now replaced the boiling point elevation constant with the freezing point depression constant. And again, only depends upon the solvent. So for water, this is going to be about 0.186 kilograms of solvent per degree Kelvin per mole of solute. And so again, this is a classic way to try and figure out the molecular weight of a solute. If you know how much mass you added, you measure the change in temperature, you can figure out moles. And so it's often used a lot as an analytical technique, but you probably more accurately know this as the idea that if I throw salt onto a sidewalk with ice, you'll note that that ice is a little bit easier to melt because you've changed its freezing point. So let's go ahead and figure out exactly how much adding a substance will end up changing the freezing point. Freezing point and boiling point for a common liquid like water. So let's say I add 10 grams of glucose. So this has a molecular weight of 180 grams per mole. So you'll note that even by adding 10 grams, we haven't added that many moles of glucose. So let's say I add this to 1 kilogram of water. So in this case, my molality is going to be 0.56. And we know both the boiling point elevation and freezing point depression constants for water. So let's go ahead and plug this in for the boiling point. So we'll end up increasing the boiling point by about 0.03 Kelvin. So not by that much. So the boiling point will end up going from about 100 degrees C to 100.03. So it is worth noting that when your grandmother says throw salt in the in your pot of boiling water for your pasta, it will make it boil faster. It actually makes it boil slower because you have a higher boiling point, and you'll notice it doesn't increase the boiling point temperature that much. That said, it can help cook your pasta a little bit quicker because the water's a little bit hotter, but you'll do far better to put the lid on it. So we can do a similar thing for freezing point depression. And here you're going to notice we have a much bigger effect because the freezing point depression constant for water is about 3 times the magnitude of the boiling point elevation. For other solvents, it's not quite this profound, but in general, the freezing point depression constant will be a little bigger. So in this case, we're going to end up depressing the freezing point by about 0.1 degrees. So this means that ice will start melting about 0.1 degrees Celsius. As we're going to see later, if you have a substance that can put more solute per gram into the solution, we're going to have much bigger effects. But you'll notice in general, a lot of these effects are fairly minor, but large enough to have some fun consequences like boiling your pasta and melting your ice. Next time, we're going to go ahead and take a look at another colligative property as we examine osmotic pressure and how to clean your water. Until then, take care.